Column is a vertical member. It is also named as strut. It is defined as a member of a structure subjected to axial compressive load. The column or strut may be square, circular, rectangular, T-shape, and channel section. Column, it is particularly mentioned as the definition of the column. It is a vertical member or vertical slender bar subjected to an axial compressive load and fixed rigidly at both the ends. Column is also known as stanchion or pillar. We commonly hear about pillar. In our term, we should mention it as column or strut. So what is the similarity between column and strut? Strut is a member or slender bar in any position other than vertical, subjected to a compressive load and fixed rigidly or hinged or pin joint at one or both the ends. The vertical member, whichever is column, strut is not only a vertical member, it is also fixed rigidly or hinged or pin joint. Example, roof truss, piston rods and connecting rods. We know length, the whole span, and which supports. What is meant by unsupported length? Unsupported length or actual length of the column or strut is a clear distance between the end restraints. Between the end, the actual length is known as unsupported length. Even if it is supported or not, the actual length of the column is mentioned as unsupported length. Then what is meant by effective length? The distance between adjacent point of inflection is known as effective length. Radius of gyration, the distance such that its square multiplied by the area gives moment of inertia of the area about the given axis. If k square is equal to 1, k is known as radius of gyration. K is equal to root of I by a. K square is equal to I. A is the surface area, K is radius of gyration, I is moment of inertia. By squaring the value, we get radius of gyration. Slenderness ratio is equal to unsupported length by least radius of gyration. This is what the definition. The ratio of actual length or unsupported length to the least radius of gyration is known as slenderness ratio. This is equal to L by K. Buckling factor, ratio between equivalent length of column to the minimum radius of gyration. Equivalent length is normally length is measured as L. The equivalent length is measured as LE. Equivalent length, which is most appropriately equal, is known as LE, but about the minimum value, minimum radius of gyration, K. Buckling load, the minimum limiting load. We know about bending moment or compressive load, tensile load. In the column, we mentioned it as buckling load. The maximum limiting load at which the column tends to have lateral displacement as buckle is called as buckling load or crippling load or critical joint. So as we mentioned as compressive load, tensile load, in column we mentioned it as buckling load. Safe load for the column is a load under which the column will not buckle. If the column doesn't buckle, it is mentioned as safe load. It is a load to which a column is actually subjected to and it is well below the buckling load. Safe load is equal to buckling load divided by factor of safety. Buckling load is not a safe load. Safe load is equal to buckling load divided by factor of safety. What are the term we are going to, for example, if we give factor of safety is 1.5, the buckling load is divided, we get safe load. Classification of column based on the slenderness ratio or length to diameter ratio. Very first one is short column. Column which have less than 8 times their respective diameter or slenderness ratio less than 32. This mentioned as short column or stocky struts. 8D, 8 into diameter or slenderness ratio less than 32 is mentioned as short column, subjected to direct compressive strengths only, and the failure occurs purely due to crushing. Medium column, 8 times the diameter to 30 times the diameter, 8 to 30, which is less than 30 short column. 8 to 30 is mentioned as medium column. The slenderness ratio lies between 32 to 120 is mentioned as medium size column, subjected to both buckling as well as direct stress. Long column, which is more than 30 times the diameter and slenderness ratio more than 120 is mentioned as long columns, which is subjected to buckling stress only. Classification of column based on load. Based on the load acting on the columns are classified into two types, axially loaded and eccentrically loaded. Axially loaded is mentioned as the axis point, whether maybe the horizontal axis or vertical axis. That axis load is applied on the axis line. Exactly at the center of the column is mentioned as axially loaded column. If it is acted eccentrically, there are some conditions. If the end condition, both ends pin joined or hinged, the effective length will be L is equal to L. L is the actual length. LE is equivalent length. We are equalizing the value. Eccentrically which means it can be acted away from the centroid. It is not on the axis, away from the axis. So it is mentioned as eccentrically loaded column. The second case, other end fixed and one end fixed and other end free. Length may be changed to 2 into L. If the actual length is given as 6, for first condition, one end pinned, another end joined, LE will be same 6. For second condition, one end fixed, another end free. Actual length is 6, so 2 into 6, effective length will be 12. One end fixed, another end pin joined, LE is equal to L by root 2, 6 divided by root 2. Both end fixed, 6 divided by 2, the effective length will be 3 meter. So this is how you should remember the 4 cases. This is very important, which we substitute in the formula. So the cases, based on the cases, the effective length gets changed as L, 2L, L by root 2 and L by 2. The assumptions made in the Euler's theorem. So this is Euler's theory of long column. We are going to make some assumptions. The cross section of the column is uniform throughout the length. If a broad material or a product you cut wherever you cut, the cross section will be same. Material of the column is perfectly elastic, homogeneous and obeys Hooke's law. If the material is elastic, it is of the same material throughout the cross section and it obeys Hooke's law. Stress by strain is equal to constant. So this is applied. This kind of theorem will be applied to those columns. The length of the column is very long compared to its cross-sectional dimensions. The column should be initially straight and the compressive load is applied axially. The failure may occur due to buckling alone, not other load. The self-weight of the column is negligible. What are the limitations we can find? It takes no account of direct stress. It means it may give a buckling load for struts for an excess of load which they can withstand under direct compression. It's applicable to an ideal strut only. In one case it is no account of direct stress and other point is it is applicable to ideal strut only, that is always worked in the column and the load applied may not be exactly coaxial. So here we can see the sign convention. If it is above, it is convexity. If it is in a concave, it is negative point. So by the previous value of effective length, we are going to substitute. So I've said which is more important, the cases we have to remember. If the both ends are hinged, the actual formula will be pi square E by L square. But the effective length pi square EI by LE square. We are going to substitute the value of LE in the actual length. The formula is pi square EI by L square. We know the effective length for the cases, we are going to substitute. So see, in the effective length, the formulas are same, pi square EI by L square. But in actual length, the term varies. In the case 2, one end fixed, other end free, LE is equal to 2L square. So it is termed as pi square EI by 4L square. In the third case, one end fixed, another end hinged, pi square EI by LE square. LE is equal to L by root 2. So it is mentioned as 2 pi square EI by L square. If both ends are fixed, effective length is pi square EI by LE square. LE is equal to L by 2, so 4 pi square EI by L square. The formula which we use for the further problem, you're going to solve the problem based on these formulas. So we know the formula, stress is equal to load by area, strain is equal to change in length by original length, Young's modulus is equal to stress by strain, area of rectangular section is equal to B into D, Area of circular solid section is equal to pi by 4 d square. For hollow section, it is pi by 4 d square minus d square, which is external diameter minus internal diameter. Moment of inertia for xx condition pd square by 12, for yy condition b cube divided by 12. Moment of inertia of circular solid section pi by 64 d power 4. For circular hollow section, I is equal to pi by 64 d power 4 minus d power 4. Radius of gyration k is equal to root of I by a. Slenderness ratio unsupported length divided by least radius of gyration L by k. Factor of safety buckling load by safe load, or we can write it as safe load is equal to buckling load by factor of safety. Euler's buckling load P is equal to pi square A by LE square. For both unhinged, LE is equal to L. One end fixed, other end free, LE is equal to 2L. One end fixed, other end hinged, LE is equal to L by root 2. Both ends are fixed, LE is equal to L by 2. So these are the formulas we have seen. And the deflection of simply supported beam with a concentrated load, del is equal to WLQ by 48 EI. If it is UDL, uniformly distributed, 5L WL power 4 384 EI. Outer diameter of hollow cylinder, inner diameter plus 2 into thickness. So these are the formulas we are going to use in the upcoming problems. So remember and write it down on your notebook.